Hello everybody, my name is Nicolas Aleman. Today I will be talking about the paper titled New Insights on 30-door B revealed by high-quality multi-wavelength observations. Firstly, what is 30-door B? 30-door B is actually part of a larger system known as 30-door radius, or also known as the Tarantula Nebula, which lies in the same region as the Large Magellanic Cloud in the southern hemisphere. So, what are nebulas? They are regions in space where a star has died, leaving a lot of dust and materials for the formation of new stars. They can be divided into several categories, but we will be focusing on two of them, supernova remnants and pulsar wind nebula. Supernova remnants come from massive stars that die in a brilliant show of energy known as supernova explosions. And pulsar wind nebulas are nebulas caused by pulsar and their energy, energizing the surrounding material. These are normally found inside supernova remnants. Going back to the question at hand, 30-door B is a supernova remnant with a pulsar wind nebula inside of it, in the Large Magellanic Cloud. The reason why the team of astronomers responsible for this paper decided to further analyze data from this nebula is because the Hubble images and the Chandra X-ray images show two different structures, with one not being visible in the optical spectrum. And also, because they noticed a faint X-ray shell outside of the already established bright X-ray shell, which is more in the inner part of the nebula. The team of astronomers from the National Taiwan University decided to use 5 different telescopes for their observations. First, they used the Hubble Space Telescope in the H-alpha line. Then, they used the Chandra X-ray images in the 0.5 to 0.7 kilo electron volts line. They used the Blanco 4-meter telescope in the H-alpha, S2, and O3 lines. They used the Spitzer telescope in the 8 and 24 micrometer wavelengths. And they used the Australian Square Kilometer Array Pathfinder in the 888 MHz frequency. They also used, for the analysis, the Magellanic Cloud Emission Line Survey to calibrate the images. The images gathered are the following, with darker spots being the places with higher concentrations of material in a certain wavelength. From these images, the main takeaway is the similarities between the Chandra X-ray image and the ASCAP image, and how certain characteristics are not visible in each other, mainly focusing on the X-ray shell visible in both, and the X-ray halo only visible in the Chandra telescope. Other observations are from the Hubble, where they detected narrow filaments, colored in red, but no shell structure from a supernova. As mentioned before, the Chandra X-ray images detect a pulsar wind nebula, an X-ray shell, and a faint X-ray halo on the outer edges, the last two being the most important findings. The right cross is the location of the pulsar, and the green lines are the X-ray contour lines, with the outermost being the faint X-ray halo. And now to the findings of the research. The team used 3 different diagnostic methods: diffused X-ray emissions, S2H alpha ratio, and non-thermal radiospectral index. To keep it simple and for time's sakes, these methods are normally used for supernova remnants, but because of the complex environment that 30-door B is in, the best one, by far, was the diffused X-ray emissions. Using spectroscopy methods and using the pulsar spin downtime of approximately 5,000 years as the supernova's remnants age, they determined that it is impossible for the faint X-ray halo to be where it is because, if it did come from the same supernova, it would need to travel at 4,000 kilometers per second, which would cause a mess of things. The most likely reason for this shell is that a supernova happened more than 5,000 years ago. And in conclusion, 30-door B's weird composition is due to 2 or more supernova explosions. Now, onto the press release. Overall, the press release is okay at best. It does mention the various telescopes used for the observations, but for some reason add this image, which cannot be found anywhere in the research paper and is actually edited by someone else entirely. It also encompasses roughly half of the article. Additionally, the article does not enter into too much detail of the method used by the team, which is expected since the paper uses phrases like long slit high dispersion etchal spectroscopy observations or continuum subtracted plus calibrated line images. The article does mention the possible supernova, which is why it's titled Breaking the Cosmic Code. NASA telescope starts the year with a double bang. If I were to give it a grade, I'd give it a C because it doesn't mention the imaging method or the diagnostic method, but it does mention the importance of reobserving celestial bodies with modern-day technology as new phenomena could be discovered and new questions could arise like, what can we learn from double supernova nebulas? Or did the initial supernova cause the second star to go supernova as well? Questions like these further our understanding of the universe, even if just a little, allowing for future generations to make more and more specific questions, overall amplifying humanity's understanding of reality. Thank you very much.